guys can get. So you have some kind of coordinate system like this, and I'm just going to show it slightly offset. And then you've got, it says at noon, a ship sails due north. So we have this is north. So the ship sails due north from a certain point. So the certain point is just the origin of my coordinate system. So this is going north, this is east. And we'll call this object A, this distance, the distance it's traveled along here, A. Okay, so it says that the speed of A is equal to 10 knots, nautical miles per hour. So that's the speed. And then you've got a ship that leaves later, at a later time, but from the same point, and it leaves at a course of 60 degrees east of north, which is, so the 60 degrees is relative to this east axis. So, well, actually, no, it's the other way around. East of north, not north of east. So it goes this way. So this angle is 60 degrees. And we'll say this length is B. And what they're asking for is what is the distance between the ships, or how is the distance changing? So this is the distance between the ships, and we'll call that C. And it says how fast is the distance between the ships increasing at 3 p.m. So what we're looking for is, you know, how much does this distance change? dc dt, right? What is the change in distance between the 2 points, the two ships? And it says, hint, use the law of cosines. So the law of cosines says that c squared equals a squared plus b squared plus, or is it minus? I got minus, I guess it's minus 2ab cosine of theta. So that's our geometric relationship. So what you're going to do is you would take the derivative of this with respect to time using implicit differentiation. The cosine is constant, so you don't have to do any differentiation with respect to theta. But here you will have a product, so you'll have to use the product rule. So when you take the derivative of that whole thing with respect to time, you'll get a dc dt, a dA dt, and a dB dt, right? Well, v sub a is one of those terms. Okay, I'm not going to tell you which, you can figure it out. And dB dt is also given in the problem. Obviously, they're the speeds. And then the other thing you'll need to know is what are the values, because you're going to have, when you take the derivative here and here and here, you're going to end up with, and also here, you're going to end up with needing to know A, B, and C. So you're going to use law of cosines to find C. So the distance A is just going to be equal to V sub A times the time, and the distance B is going to be V sub B times the time. And these are given, and these times are not the same because they leave at different points, but you can figure out what those are. Okay, so what you'll do is you find A from the velocity of A and how much time it spends in the problem. You'll find the length B by the velocity of B times the time that B travels. You can find C using this relationship, and then you can take the derivative of this with respect to time to find the relationship between dc dt, dA dt, and dB dt. And the only thing that you won't know is this thing. That's the unknown. And you can find everything else just as I showed you. So give that some thought. Read the problem. and see how far you can get. You can talk to your neighbors about this if you want to. So these are distances. These are 10, 15 knots. You see one leaves at noon. They're both, it says, at 3 o'clock. So the final time is 3 o'clock. So one will travel for so long, the other one will travel for a little bit shorter time. It's probably like, this is too much like physics. I think what I'm going to do is, while you guys are getting started on that, I'm going to Nope. Okay, so we'll give you a little help here. So let's see. Got to turn my thing on. So we have the distance A. So how long has vessel A traveled? I already wrote the number down. I was too quick there. So you got 3 hours at 10 knots, and those are nautical miles per hour. So this has traveled 30 nautical miles. Okay, so do the same thing for B, and then use this to find C. So now that I've given you part of it, and also you want to go ahead and take the derivative of this expression with respect to t as well before I tell you how to do it exactly. So this one travels 2 hours because it leaves an hour later, and it travels at some other speed, which you can read from the problem. So actually, it travels for less time, but it travels the same. Actually, the distance is the same. So go ahead and plug those into here. It's funny how little we use the law of cosines and the law of sines. I can't remember. Probably on one hand, I've used the law of sines and cosines in my life. I've used right triangle geometry a bazillion times, but the actual law of cosines, it's interesting, but it's not used that much. I know the answer now. I'm not going to tell you what it is yet, but so where are you on this? Okay, so you got C correctly. Yes, and you also did this. Let's see what you got. So you've got to include the dCdt here and the dAdt and the dBdt, and so all of these are going to have, these three are going to have the corresponding derivative, because C is, and actually, yeah, you shouldn't have those there. You should just have the derivative of C squared with respect to T, the derivative of A squared with respect to T. So you want to erase those things. When you do the product, you'll have, that's correct, except this should be minus 2, I think. And you also have to remember the cosine. So those two should have the cosine. Anyway. So it turns out it's an equilateral triangle, since also this turned out to be 900, and so the square root of 900 is 330. Okay, now over to here. So when you take the derivative of c squared, you get 2c, but because it's implicit with respect to time, you have a dc dt part. And the same way with these two. So you'd have 2a dA dt plus 2b dB dt. Okay, so these are not products. And then you'd have negative 2 cosine theta times the derivative of this, which is a product. So you'd have the first term times the derivative of the second plus the second term times the derivative of the first. So that's your result. And you can see that what we're trying to solve for is dc dt. And we've already calculated c. We know a, dA dt is 10, and dB dt is 15. That's the rate of change in the distances, which is the speed. I guess we can get rid of the 2, so we don't include that. Theta is 60 degrees. So everything on the, we'll end up dividing by 2, which will cancel out the 2's, and we need to divide by c to solve for dc dt. So plug everything in there and see what you get. So what we're saying is that dA dt equals 10 nautical miles per hour, and dB dt is 15 nautical miles per hour, and theta equals 60 degrees. And what else do we know? We know A is 30 nautical miles, B is 30 nautical miles, C is 30 nautical miles. And while you're coming up with the answer, I'm going to hand out one more. I decided to do 2 more problems. Okay.
Why is the negative 2 cosine, like when we get the derivative of that, why is it negative 2 cosine?
Well, you've got the 2 cosine theta is like a constant, so it's the constant multiplier rule. So when you would take the derivative of the part that's actually varying, which both A and B are varying, so that's the part I take the derivative with respect to. The rest of it's just like 2 cosine theta is just just like 4 or 6. So I don't take the derivative of that part. You only take the derivative with respect to the parts that actually are changing.
Oh, okay.
This is much more difficult than you'll see in the test. So hopefully you're gonna look at some problems that are harder than you do, and hopefully when you do the one for your test, you'll be like, oh, this one's easy. It's kind of like training, well, actually that's not true, because like cross country, you train hard and then you really run hard and you throw up because you're running so hard. At least if you're running really hard. those in. So. So I got 12.5 nautical miles per hour. Anybody to get that? Yep. So it makes, I mean, it should be getting bigger. So at least the sign's correct. So I got 375 inside the parentheses, and I divided by 30, which was this part, right? So I divided by C, that's that part. And then the rest of it was A times dA dt plus B times B dt minus cosine of 60 degrees times A times B dB dt plus B times dA dt. Okay, so you guys can turn that in. So let's look at 2 more problems here. This is number 37. It says the endpoints of a movable rod of length 1 meter have conditions x, 0 and 0, y. The position of the end of the x-axis is 1/2 the sine of pi t over 6, where t is the time in seconds. Find the time for 1 complete cycle of the rod. So that's not calculus, that's from pre-calculus. So does anybody have any idea of how we would find the time for 1 complete cycle of the rod? Evan. What is the time for part A? Find the time for 1 complete cycle of the rod based on the information that's given. Have any idea? Yeah, so what is the argument of the trig pi, what does the value of the argument of the trig function have to go from to what to get a complete cycle?
Well, the argument would have to go from 0 to 2 pi.
Right, okay. So that would mean that if t equals 0, you get 0. So time goes from 0 to, the question is, what does t have to be to get the argument to go to 2 pi? So all you have to do to answer the first question is set pi t over 6 equal to 2 pi and solve for t. because if you look at the argument, it's pi t over 6. At t equals 0, pi t over 6 equals 0, because you just multiply by 0. Then at t, well, the question mark, what does t have to be so that pi t over 6 equals the other part of the entire cycle, which is 2 pi. So t equals, and I guess we'll assume they're seconds. Yeah, it says seconds. So Cassie, what's t? 12 seconds, yeah. So the pi's cancel out, multiple by both sides by 6, so you get 12 seconds. So that's the time for one complete cycle. What is the lowest point reached by the end of the rod on the y-axis? So if you look at that arrangement, so here's the origin, and this distance is x, and this distance is y. Let's see, Kelly. So what is the value? Well, let me ask you this question. What is the maximum value for x? Look at x of t equals 1/2 sine of pi t over 6. What's the maximum value of the sine? Goes between 0 and
12.
No, sine. Just remember the sine function. What's the sine of 90 degrees? Okay. Yes, good. Okay, so the maximum the sine can take is 1. Therefore, the maximum the value that x of t can become is 1 times, based on this thing. So the sine can only be 1. That's the maximum value. So you're going to multiply it by 1/2. So the maximum value of x is going to be 1/2, right? Okay. So the maximum value of x is 1/2, and then that's going to tell us what the minimum value for y is, because this is going to, so what we're going to say is, so x equals 1/2. This length here is 1. So the question is, what is y? So you use the Pythagorean theorem there. It's not 1/2. Okay. So it's not symmetric, even though it looks like it's symmetric. What you need to do is solve for y. So, y squared plus 1/2 squared equals 1 squared. So solve for y. And we get, let's see, Mark, what do you get? What's that? Square root of 1 point, I don't know. Let me try, 0.125 square root. No. Okay, so what you can do is you take 1 squared, which is 1, subtract 1/2 squared. 1/2 squared would be 1/4. So 1 minus 1/4. So what you get is y squared equals 0.75. And then you take the square root of that. So what's the square root of 0.75? Mark. Take the square root of 0.75. Okay, anybody recognize that number? So square root of 3 over 2. Okay, so anyway, so that's what is the lowest point reached by the end of rod in the y-axis? The answer is 0.866. Okay, now it says find the speed of the y-axis endpoint when the x-axis endpoint is 1/2, 0. So what we need to do is figure out what is the y position as a function of time, and then take the derivative of that, and that'll give you dy dt. So now we got to figure out what is, if x of t is equal to 1/2 the sine of pi t over 6. Actually, I don't think we have to. We could use the just use the Pythagorean theorem here, because y squared plus x squared equals 1 for the entire time. So that would probably be the way I would do it. You just use the Pythagorean theorem. So x squared plus y squared equals 1 squared. So we've done that before. Take the derivative of that with respect to time. We know what x is. In this case, x is 1/4. So we should be able to calculate y from this relationship. I'll let you do that. I'm not going to work the whole thing out for you. The question is, you'll find out that when we take the derivative of this, we need to know what dx dt is. And in previous problems, we've been given that. So Margaret, how do you think we get dx dt? Yes, exactly. So you're going to get x, and then you plug in x equals, or t equals, well, that's the question, what is t? I guess what you would have to do is you would have to find out, given that value of x, what is the value of t, and then you can apply that to the derivative. So there's two other things you're going to have to do here. Is for x equals 1/4, what is t? You might not think we need that yet, but we do need to know what that is, because when you take the derivative of x with respect to time, you're also going to end up taking the derivative of this thing, 1/2 the sine of pi t over 6 with respect to time. And that's going to be a function of time, not a function of x. So you're going to need to find the relationship between dy dt and dx dt. You're going to have to take the derivative of that. You're going to need to plug in 1/4 into here to get y. You'll also find out that you need to know what dx dt is. To do that, you're going to need to figure out what value of t gives you x equals 1/4. And also, you're going to need to find dx dt by taking the derivative of this with respect to time. So I would do them this. So that's step 1. Take the derivative of this with respect to time. Step 2 is to use the Pythagorean theorem to solve for y. Step 3, well, let's figure out what time is to get x equals 1/4, and between 0 and 2 pi. Well, between 0 and a period, whatever a period is here. And actually, there's going to be multiple, I guess the smallest time makes that happen. And then take the derivative. You have to use the chain rule to take the derivative of that thing with respect to time. So give those a try, and again, you can talk to your neighbor if you want to, or you can ask me questions if you You should be able to do the first couple ones. This one you may have to think about a little bit. Again, this is much more difficult than I put on a test, so just think of this as a challenge. Okay, so let's make sure you do that right. Okay, so that is correct. So we need x, which we have. We need to calculate y. We also need to get dx dt to solve for dy dt. So the next, did you already solve for, have you solved for y yet? What'd you get? 0.968. Yeah, that sounds about reasonable. So now you need to figure out what value of t gives you an x of a quarter. So that's pre-calculus kind of stuff. You know, you got to solve your... It's probably going to be a first quadrant solution, so you should be able to just use the inverse sign. So just what you're going to do is you set x equal 0.25, divide by a half, take the inverse sign, and then multiply by 6 and divide by pi, and that'll give you the time. So it's not that complicated. Just use the simplest approach. There are multiple times where you get x equals a quarter, but that's we're just worried about the one particular time. And I picked this one because, you know, this is real world kind of stuff wherever it is on the paper. If you're a mechanical engineer, this looks like something that looks like a pretty believable mechanism, and typically the ends do move in a sine or cosine relationship, and you do want to relate the velocities of the two parts to each other. So I thought this is actually pretty good. Okay, so what I'm going to do is add a page and start a little bit here. So let's see here. What are my units? Did they give us a dis? They didn't really say what the units were. Oh, meters, yeah. So Cass has got the first two parts right. That's good. Now make sure you've got to do this in radians and not in degrees, so you probably probably did it in degrees, but we're dealing with, usually when you're dealing with something that's rotating, you deal with the radians. So what have I got? Inverse sine of a half. Oh, is that it? 1 second? Looks like it. Did you get 1 second for t? Nobody's saying no, so I'm assuming you did. So next, the last part is this derivative. So dx dt equals 1/2 times. Anybody get that answer? Okay. I'm not sure if that's correct, so we'll go through the procedure and you can tell me if I made a mistake. So let's go back up here. So we use the Pythagorean theorem to solve for y when x equals 1/4. Then what do? Oh, figure out what time is so that x equals 1/4. So x is 1/4 is equal to 1/2 sine of pi t over 6. When you divide by a half, same as multiplying by 2, so that becomes 1/2 is the sine of pi t over 6. And then you take the inverse sine of both sides using radians. So the inverse sine of 1/2 is 0.526, which apparently is pi over 6 if you use the unit circle. So this turns out to be pi over 6. So if you solve for t, you get t equals 1 second. So after 1 second, it's moved 1/4. And that makes sense because if you think about it, if I go back up, where's my function? This one right here. If I let t equals 1, the sine of pi over 6 is a half. A half times a half is 1/4. So that agrees with what I would have expected. So the time, and then what I do is I take the derivative with respect. I need to find what dx dt is, because that's part of my, when I did the implicit differentiation, That's what I'm trying to solve. Well, this is what I'm given. I want to solve for what is dy dt. So I need to know what this is. I know what x is. It's 0.25. I know what y is. And therefore, I need to take the derivative of that. So where is this? Somewhere here I did it, I think. Where did I have it? Okay. Huh. I thought I did it somewhere. That was on this. Must have been over here. No. Oh, here. Oh, it's right here. Okay. Yeah, so taking dx dt is I take the derivative of 1/2 sine of pi t over 6. So the derivative is 1/2. The chain rule says you take the derivative of the sine, which is the cosine, you keep the argument the same, and then you multiply it by the derivative of what the argument is. So the derivative of t is 1, so the derivative of pi t over 6 is pi over 6. So that's the chain rule part. The half comes from, that's the amplitude. This is the derivative of the inside. So that's dx dt, and then I found out that I was at t equals 1 second, so I plug in t equals 1 here, so I get the cosine of pi over 6, which is the square root of 3 over 2, which is 0.866, so I multiply all that out, and I get 0.227 meters per second. So that's dx dt, if I did that right, 0.5 times pi divided by 6 times 0.866. So that's 0.2, that's correct. And then I do my implicit differentiation, cancel out the 2's, solve for dy dt. So I get x dx dt. When it goes to the other side, it becomes negative, and then I divide by x. I divide by y, and then I plug in what I know. X is 0.25 meters, y is 0.968 meters, dx dt is 0.277 meters per second. You multiply all that together, and you get negative 0.059 meters per second. Okay. Again, well, let me just ask you the question. Now that I've explained it to you, how many people understand what I did? Ish, yeah, you get it. Okay. I mean, it all comes back to the same thing. You need some kind of geometric relationship, which in this case was the Pythagorean theorem. You need to know something about the rate of change of either x or y. That was the extra part. The hard part here was having to use the sine function and take the derivative. Okay, the next one's actually easier, so let's kind of set that one up. Even though it is a larger number, it is still. So what we have is a fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle between the line and the water changing when there's a total of 25 feet of line out? So what dimension on the figure is 25 feet? It's x, obviously, because it's not theta. Okay, so that's 25 feet. What kind of triangle can we draw? If we draw from the tip of the fishing rod straight down and then over to where the fish is at the surface, it's a right triangle. So it's going to be right triangle geometry. Because they're asking for theta, it's not going to be the Pythagorean theorem to find, it's going to be a trig function. In this case, the trig function is not going to be the tangent like it was before, but it's going to be which trig function? Let's see. Xavier, which trig function do you think I'd use in this case, based on where the angle is and where the 10 feet, which stays fixed? Sine, yep. So if we draw our picture, it's going to look something like this. So this is our angle theta. This is the fixed length, it's 10 feet. This is 25 feet. And the relationship is that the sine of theta is equal to 10 divided by x, opposite over hypotenuse. And it says, at what rate is the angle between the line and the water changing when there's a total of 10? Okay, we're reeling in at 1 foot per second. So what is equal to 1 foot per second? Something derivative with respect to time of something. So let's see here. Christian. Pardon me? Yeah, okay. So remember this distance here is x. So it says the fish is reeled in at a rate of 1 foot per second. So which dimension is he reeling in? Which part of the triangle is the fishing line? X. Yeah. So 1 foot per second is equal to d something dt. dx dt, right? Okay. So dx dt, and is it positive or negative? Yeah, because he's reeling it in, so it's getting shorter. So this is the relationship. So you have to take the derivative with respect to time. So we take the derivative with respect to time of the sine of theta is equal to the derivative with respect to time of 10 over x. So the question is, how do you, this one we've done before, it's going to be equal to the cosine of theta times d theta dt, just like we had the tangent before. What do we need to do to this before we can take the derivative?
Why can't you just put 25 in as x?
Pardon me?
Why can't you put 25?
Well, you can, but we will do that at some point. But we need ultimately, when we take the derivative of that, it's going to involve x and dx dt. So that's why we can't just plug it in there, because it's x. It's 25 at a particular time, but it's not 20. It's not 25 every time. It's getting shorter. So that's why we can't just stick it in at this point. So we need to take the derivative first. So what do I do if I told you to take the derivative of 1 over x with respect to x? What do I have to do to that before I can take the derivative? Yeah, right. You got to move it to the numerator and make it a negative. So you do the same thing here. You'd say the derivative with respect to time of 10 times x to the minus 1. And remember, when you're doing implicit differentiation, it's just like normal differentiation, except you add dx dt at the end. So what is so the derivative? So I got to rewrite this. So the derivative with respect to time, or with respect to x, of x to the minus 1 power is just going to be negative 1, the exponent, times x to the minus 2 power. So what do you think I should put up here? Negative 10, x to the minus 2 times, dx dt. So if let's just rewrite everything we have. Cosine of theta d theta dt is equal to negative 10. I'm going to move this to the denominator times dx dt. So now so that's the derivative. And so you can see that when we take the derivative, we can use 25 here, but we also need to plug in dx dt, which we calculated, or it's given in the problem. So we know this, that's 25. This is whatever the 1 foot per second. The cosine of theta, how do we get the cosine of theta? You have to use the Pythagorean theorem to get this. The cosine would be this length divided by that, or this length divided by that length. So you'll need to calculate, what do we want to call this, y? I know it's not y, but it's not a vertical displacement. We can call it anything we want, but you'd have 10 squared plus y squared is equal to 25 squared. And so once you solve for y, then you could say the cosine of theta is going to be equal to y over 25. So then you have that. And this is what we're trying to figure out. What is d theta dt? So what we'll do next beginning of class tomorrow is we'll just finish this out, because you can calculate y from the Pythagorean theorem. You can calculate the cosine of theta. Once you have that value, then you can solve for d theta dt, and we have everything in there, and we can get the answer. Okay, and the answer is going to be in radians per second, not in feet, not in degrees per second.